Alright, welcome everybody to this physics workshop with the ROATAN Dive Academy. My name is Fabio Buitrago, I'm the course director with ROATAN Dive Academy, and I'm going to be working with you today on one specific topic of the physics you will need for your Dive Master course or for preparing you for IDCs. When you're ready to take your IDC, you're going to use this information to get ready, study and practice. So I'm going to give you some explanations on how the calculations and the numbers are done in this topic of the physics, which is specifically related to the Archimedes Principle. We apply that information when we are lifting objects from underwater. So we're going to be talking about positive forces, which is the Archimedes Principle, and how to add or subtract air from a lifting device to bring objects to the surface. Right, this is the first of a series of workshops that we're going to be conducting with the ROATAN Dive Academy for you to study, practice, or just to keep fresh all that information that you may have acquired during your courses, Dive Masters and IDCs, and maybe you just want to refresh during these lockdown times that we are safe at home, but we can use the time efficiently by practicing, refreshing, and remembering, for those of you that have already taken the IDC, remembering how to do these calculations. So we're going to be talking, as I was saying, about the Archimedes Principle, and you can find that information on the Encyclopedia of Recreational Diving in page 419. You will find here all the information related to the Archimedes Principle, which is what we're going to be talking about. So let's read from the encyclopedia what is the Archimedes Principle. I'm going to write it down here on the board so you can read with me. An object wholly or partly immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. What does that mean? It means that every time we put an object in the water, the volume of the object is going to displace the water that now the object is using within a recipient, right? So I'm going to show you exactly that using these glasses that I have here, right, and a bottle of water, and I have two objects. I have one light object. In this case, this is a fruit that we call anicaco here in ROATAN. This is a tropical fruit. And we also have a rock, right, that is heavy and has, let's say, a bit more, but almost about the same volume as the fruit that we have. So I'm going to place, for you to see, I'm going to place this glass on top of this cup, right? So we're going to fill this glass, we're going to fill it completely with water, so no single drop can go in the glass. And then I'm going to place the object on the inside to see how much water is displaced, and you will see the water displaced on the lower section of this cup. So let's put these objects here. You may want to come closer so you can see. Okay, so I'm going to put this glass here on top of the cup, and then I am going to fill the glass all the way to the top with fresh water. Okay, so here it goes. I have to fill it all the way so no more water is, so the glass cannot contain an extra single drop of water, so it's completely full all the way to the top. There you go. Okay, so what would happen if I put the rock? The water is going to be displaced, right, by the same volume of the rock. So here it goes. You can see now the water is on the glass is still all the way to the top, but there is a large amount of water down here, which is the water that was displaced by the object. So this is the volume of the object. And according to the Archimedes Principle, the force that that object is experiencing up, that is buoying up the object, is the same as the weight of the water that the object has displaced. So I'm going to take this glass off, and first we're going to weight the water that the rock displaced. So you can see here 0.1 0.01 kilograms. 0.01 kilograms is the positive force. Okay? I'm going to take the rock out now. Just drop the water here so we don't make a mess. Okay, I'm taking the rock out and we're going to weight the rock. So you can see it's more than what the weight of the water. Basically, we're talking here about what would be 0.15 maybe. So the rock is heavier than the weight of the water that was displaced. Therefore, the rock sinks and goes to the bottom of the glass. Now, let's apply that information to some exercises that you would be receiving on your exams during the Dive Master and the IDC courses. Let's go back to the board. Okay, so here we are back, and now we're going to have the first of the exercises we're going to be working on during this workshop. And first we're going to start working in fresh water, because the weight of the fresh water is 1 liter weighs 1 kilogram, so it's easier to calculate for you to understand the principle, and then we can apply that in following exercises to salted water to see how to convert kilograms to liters and liters to kilograms. Okay, so let's write the first question that we have here. And it says, how much gas should be put in a lifting device to bring to the surface an object that weighs 10 kilograms and is in fresh water, right, and displaces 6 liters of fresh water. So let's start by putting all the information we have here on the board, right? So what would be the displacement? Displacement, 6 liters, right? We're talking about fresh water, so I'm going to write FW here, and then the weight of the object is 10 kilograms, right? So now we have all the information. We're going to work with this information now. In the way I like to do it is with a graphic. So I'm going to make the graphic of an object here, and I'm going to have two forces. One force, which is the negative force, is going to be the weight. So this object is being pulled down by a negative force of 10 kilograms, right? And now we have a displacement of 6 liters. As we saw before with the glass, the water displaced is what we have to weight to convert the liters to the kilograms that are going to be the positive force, or the Archimedes force. So in this case, 1 liter of fresh water weighs 1 kilogram. So it is very easy to convert liters to kilogram because it's 1 to 1. So 6 liters of water being displaced are going to weight 6 kilograms. So I'm going to put those 6 kilograms as a positive force on my diagram here. Right? So now we have all the information. We have the weight, which is 10 kilograms, is negative, and now we have converted the displacements, liters, into kilograms, which we know because by the Archimedes Principle, that is 6 kilograms positive. So if we had to add up these two forces, what would be the result, the balance of the two forces? So we have 10 negative and 6 positive. The balance would be minus 4 kilograms, right? Because this force is larger, so it's going to be negative, and it's going to be minus 4. Okay, so the question is asking us how much gas should be put into a lifting device to bring this object to the surface, to make it neutrally buoyant. So now what we need is to convert these kilograms of the resulting forces. We need to convert those to liters so we know how much gas, how much air we have to put into a lift device. And we know 1 liter of fresh water weighs 1 kilogram, right? So the answer would be 4 kilograms are going to be the weight of 4 liters. So for putting this object neutrally buoyant, or to bring this to start the process of bringing this object to the surface, we need to add 4 liters of air to a lifting device? That's the answer to the question. Okay, let's do one more skill. Let's do one more exercise, right? In freshwater as well. So you can apply this information to a different object, right? So I'm going to leave this I'm going to leave the graphic there. Okay, and we're going to put the information for the second exercise we're going to do. So it says, how much air should be put in a lifting device to make an object that weighs 122 kilograms and displaces 87 liters of fresh water in neutral buoyancy? Okay, so what we're going to do for this is we're going to just put all the information we have from the question to the graphic. Right? So we know the weight is going to be a negative force and is 122 kilograms. Right? And then the displacement is 87 liters. That in fresh water we know 1 liter weighs 1 kilogram, so 87 liters is going to be 87 kilograms. And that is going to be a positive force because of the Archimedes Principle that we discussed before. That is the weight of the water displaced, so it's going to be a force that is buoying up the object. If we add all these two, we come out with a resulting force that is going to be negative because the majority, the larger force, is the weight. Right? So it's going to be negative and it's going to be 35 kilograms. This number comes out of 122 kilograms minus 87 kilograms. And we know it's negative because this is the largest force. Okay, so now for answering the question, what we need is to convert this 35 kilograms to liters so we know how much air should be put into a lifting device to make that object neutrally buoyant. And as we know 1 liter weighs 1 kilogram, 35 kilograms would be the resulting weight of 35 liters. So the answer for this question is 35 liters. That's what you need to put in a lifting bag, in a lifting device to make this object neutrally buoyant. Okay? Let's do one more in fresh water and then we start working with salted water. So I'm going to put all the information again right here. Okay, so let's read the question first, and I'm going to write the question here in the board. It says, how much weight should be added to an object that weighs 34 kilograms and displaces 45 liters of fresh water to be able to sink the object? Okay, so let's put the information here on the board. So we have the displacement. So displacement is 45 liters. Right? We are in fresh water, so we're going to put FW here, and we know the weight of the object is 34 kilograms. Okay, so now we have all the information that the question has given us, and we're going to put all that information in the graphic. Okay, so we have an object that has a negative force, which is the weight, of minus 34 kilograms. And we have a positive force, which is 45 liters in fresh water are going to be 45 kilograms, right? So 45 kilograms. Okay, so now the largest force is the Archimedes force, the force pulling the object up. So the resulting force is going to be positive because this is the largest force. So if we subtract 34 from 45, we will come to a number of 11 kilograms, right? Meaning that this object doesn't sink. It floats because the resulting force is positive, so the object is going to be floating, right, at the surface. And the question is asking us, how much weight do I need to add to the object to sink it? So basically, what I need to add is the same force that is pulling up the object to make it neutrally buoyant, so I will need to add 11 kilograms of weights that are going to be negative, right, because it's weight. So if we add 11 kilograms to this object, we are going to make it neutrally buoyant, so we can start sinking the object, and that would be the answer to our question. Okay? So let's move now to the same set of exercises, but let's do some in salted water, so you see how the conversion are made in salted water, where we have a different weights of the water. So I'm going to write down here the question, so let's read it. How much air should be put in a lifting device to bring to the surface an object that weighs 73 kilograms and displaces 49 liters of seawater? Okay, so I'm going to put the information now here on the board. We have a displacement of 49 liters, right? We are now in seawater, salted water, okay? And the object has a weight of 73 kilograms. Okay, so how much air do I need to add to a lifting device to make this object neutrally buoyant? I'm going to make the graphic again. Okay, so we have the object here, and we're going to have a negative force, which is the weight. So this is going to be minus 73 kilograms. Now, we need to write down here the positive force, but now we are in salted water. And if the object displaces 49 liters, what will be the weight of 49 liters of seawater? So instead of working one-to-one as we were doing in freshwater, now we know that 1 liter of seawater weighs 1.03 kilograms, right? So we can come out with the number that we're going to be using, which is 1.03 kilograms per each liter of salt water. Okay, so if 1 liter weighs 1.03, 49 liters, how much will they weigh? So we just have to multiply these two numbers. And how do you know we have to multiply or divide? Always put the units. I'm going to show you here. We have 49 liters, right? If I multiply times 1.03 kilograms per liter, then I can cancel the liters here, and I'm going to have a resulting unit of kilograms. If I were to divide, what will come out is something like liters over kilograms over liters. That doesn't make sense, and I cannot cancel the liters in this calculation, in this mathematical operation. So it has to be multiplied so I can cancel the liters, right? So if we do 49 liters times 1.03 kilograms per liter, on the calculator we will come to a number of a positive force of 50.47 kilograms, which is what we're looking for. And just for you to know, I'm working in the metric system, because it is easier to make the calculations. For those of you working in imperial, you will need to calculate 62.4 pounds per cubic feet or 64 pounds per cubic feet in salted water or in fresh water. So the calculations are different because of the numbers you have to use. So in this case, 1 liter is 1 kilogram in fresh water, and 1 liter is 1.03 kilograms in salted water. So it's it's easier, right? Simpler to do the calculations. So let's go back to the graphic. So now we have a negative force, which is the weight, right? This is minus 73 kilograms. And now we have converted these 49 liters to a positive force of 50.47 kilograms, right? So now that we have the same units, we can subtract the two numbers. Don't put liters here and try to add or subtract liters and kilograms. That doesn't work. It has to be the same unit, right? So if we subtract 50.47 from 73 kilograms, we will come to a resulting force that is going to be negative because this is the largest number, right? That's the largest force of 22.53 kilograms. Always put the units. Remember, don't forget to put the units. The units are going to help you understand what you have to do. So now we have 22.53 kilograms as a resulting force. So we know this object is at the bottom of the ocean. It sinks because it's the largest force is negative, right? And it has a balance, a resulting force of 22.53 kilograms negative. So we need to convert these kilograms to liters to answer the question. Always read the question. The question is asking for volume. It's asking for how much gas, how much air do I have to put in a lifting device, and how much air I cannot answer with kilograms. I have to answer with liters of air, right? So for converting these, I'm going to write down here, we have 22.53 kilograms, right? What I need to do now is divide in 1.03 kilograms per liter. Why do I know I have to divide? We have kilograms, and I can cancel the kilograms, and I'm going to have a resulting unit of liters, right? If I would multiply these two numbers, what I will have as a result would be kilograms times kilograms, so that would be like kilogram square per liter. That doesn't make sense. So if I just add the units, I would know that I have to divide so I can cancel the kilograms. So in this case, 22.53 divided in 1.03 will have a resulting value of 21.87 liters, which is the answer to my question. I need to add 21.7 liters to the lifting bag, to the lifting device, to make this object neutrally buoyant or to start the process of bringing this object to the surface. Okay? So let's do one more in salted water, and I'm going to use large numbers so we can just imagine how that and pay attention to the differences of big numbers when we are working with salted water and converting liters to kilograms. So let's have the question here. We have an anchor. Okay, so it says how much air must be added to a lifting device to bring to the surface an anchor that weighs 943 kilograms and displaces 12 liters of salted water. Okay? So, I'm going to write the information now that we have read the question. So, the displacement is 12 liters. We are in seawater, and the weights of the object is 943 kilograms. Okay? So we're going to make our graphic. We're going to have here an anchor. Okay? This anchor has a negative force, which is the weights. And we know the weight is 943 kilograms. Right? That's a negative force that is pulling the object down. But the anchor displaces 12 liters of salted water. So how much would that be in kilograms? How many kilograms are 12 liter weights, the 12 liters of salted water? So that's the positive force we're going to add here. Okay, so if we have liters, we have to multiply So we can cancel the liters as we said before. Okay, so 12 liters times 1.03 kilograms per liter allows me to cancel the liters because this is divided here, and the resulting unit is going to be kilograms. So 12 times 1.03 is going to be a positive force of 12.36 kilograms. Okay, so now we have the two forces, the negative and the positive, in the same unit. So we can calculate the balance out of those two forces. Okay, so the resulting balance, the resulting force, we know is going to be negative because this is the largest force. Okay, so the resulting is going to be 930 kilograms, 0.64 kilograms, I'm sorry. 930.64 kilograms, negative. So now what we need to do is to convert these kilograms, that is the resulting force, into liters, so we know how much liters of air we have to put in a lifting device to bring this object to the surface. And for doing that, if we have 930.64 kilograms, we would need not to multiply, because if we multiply times 1.03 kilograms per liter, we are going to have kilograms squared. So if we cannot multiply, we're going to divide. And just to double check, this is kilograms per liter, I can cancel the kilograms and I'm going to have as a result only liters as the unit. So if I divide 930.64 kilograms into 1.03 kilograms per liter, the result of that operation is going to be 903.53 liters. And this is the answer to my question. I need to add 903.53 liters of air to the lifting device to bring this object to the surface. Okay, so with this exercise, we have already finished our workshop. I hope these exercises and this explanation had refreshed the skills or have helped you understand how to do the calculations and the conversions when we work in salted water and when we work in fresh water. Remember, this is the first of the series, several of workshops we're going to be doing during these lockdown times. So we're going to be uploading these videos in our channel in YouTube that you can just like and subscribe, and you will see all the videos that we're going to be uploading that are going to help you prepare for your IDC or for your Dive Master course, or just simply refresh all the information. If you have any questions, or if you want to know about the courses that we teach, Dive Master and IDC courses, you can go into our webpage, which is ROATAN.diveacademy.com, as you can see down here, or you can just send us an email to gopro@roatandiveacademy.com, and I will personally answer your questions and any inquiries that you may have regarding the courses. So thank you very much. I hope you have enjoyed, and see you next time.